Francisco. Yeah, the weather here is good.
Yeah, same here. I'm also in San Francisco, a little sunny today.
Same in San Francisco.
Looks like you're the only one.
I'm in Emeryville, which I think I might have used this before, but it's where Pixar Animation Studios is. If you need some kind of landmark.
Context and all that. And then, hey, Aaron, dude, where are you based out of, man?
Why does everyone have good weather? The weather here in Toronto is horrible. It's been raining the past few days, so yeah.
Oh, I'm
anyway,
sorry,
yeah,
dude.
I'm in Toronto. Yeah.
Well, it's your fault for living in Toronto. No, I'm joking. I'm so joking.
I know.
I'm so joking. No, as a Montrealer, I'm allowed saying that. I just want to call that out. Yeah, as a former Montrealer, it's okay for me to dig on Toronto. So.
All right, I think we're all set up. We're live on YouTube and we're live on LinkedIn. So welcome everyone. Thanks for joining us. Happy to have you. I think we're gonna go ahead and get started here. I just have a few intro slides and then we can get to the content. All right, share my screen. All right, so thanks everyone for joining us. This is the third part in a 4-part series with folks from Salesforce Engineering. So today they're going to be talking about global synchronization and ordering in Delta Lake. And a call out for the last part in the 4-part series is going to be in 2 weeks. So the end of April, so the fourth part is about continuous integration and continuous delivery with Delta Lake. And a quick call out to our Data plus AI online meetup group. So that's where we share all of our upcoming sessions. I also post all the links to, like if it's a series like the Salesforce series, I also post the links to the previous session recordings. And also if you go in there and join the group, you'll be notified of our upcoming events, and you can join the Zoom portion of this broadcast and you can answer polls. We always launch a few polls, and you can join us there, or you can also subscribe to our YouTube channel. I know we have some folks joining us there, so I'm happy to have you. On our YouTube channel is where we host all of our recordings. So all of our Tech Talk sessions are recorded and they are hosted there. So since this is a specific series, I'll go ahead and create a playlist. So you'll have all 4 parts right there so you can watch it really easily. But we also have our online meetups Tech Talk playlist, and also a few other cool things in there. So I invite you to check us out there and subscribe. And then also LinkedIn, of course, we hope you follow Databricks. We go live on LinkedIn too. And that's a fun space to also engage with you all. So I want to do a quick call out for Summit. As you notice my background, I love this background. I love the animation. But so we have our Data plus AI Summit coming up. So that's going to be the end of May. So May 24th through the 28th, we have some awesome speakers lined up that we're super excited about. I have some photos up there of some of our keynote speakers, Mate, Ali. We also have Malala, which I'm really excited to hear, Sol, Renault. We have lots of awesome, great speakers. And so we have over 200 sessions, which I can't believe they are packing into 5 days. But thankfully, everything is recorded and available after the conference. So if you want to register and stay up to date on notifications and when we announce new sessions, I invite you to register, and then you can always revisit sessions at a later date. So lots of awesome content. So I hope you'll join us and register. And then also I want to do a quick call out for community lightning talks. I'm still working on getting a few of these set up. We have community lightning talk sessions at Summit, which I'm really excited about. We have a lot of awesome community members that are getting lined up to present lightning talks. And then I'm going to run hopefully 2 community lightning talk sessions one at the end of this month, and then kind of early to mid-May to kind of, get ready for Summit and get excited for all the awesome content. So I have the link here and I'll drop it in the chat spaces, but I would invite anyone and everyone to submit a talk. We'd love to hear from you. We just want to see what you're working on, and lightning talks are a great kind of quick way to get your feet wet in presenting and share what you're working on and get some feedback. So topic ideas, we have a few topic ideas there, but really, it's up to you. It's up to what you're working on. So with that, just a quick reminder, the session is recorded and you're invited to ask questions. So if you're in Zoom, try to post those questions in the Q&A. That makes it a little easier for us to manage them. And then also in YouTube and LinkedIn, feel free to drop questions there. Craig, Chris, and Denny are all helping to moderate the chat spaces, it's awesome to have 3 additional folks joining us to capture all those questions. So I will go ahead and pass it off to Craig, who will go ahead and introduce the Salesforce team.
Awesome. Thanks, Karen. Just a quick introduction for myself. My name is Craig. I'm a solutions architect at Databricks. Been at the company for a little over 2.5 years. I'm really excited to be here and to introduce the Salesforce team. Heng, do you want to go first?
Yeah, my name is Heng. I work at Salesforce for 3 years. And my interest is microservices, distributed system, and big data. I'm very excited to be here to share our Delta Lake project.
Awesome. Thanks, Heng. Aaron, you want to go next?
Hey, good morning, good evening, good afternoon, everybody. I'm Aaron, based in Toronto. I've been with Salesforce for slightly over 6 years. Similar to Heng, my main interests are microservices, big data, and I'll be one of the panelists today to answer your questions.
Cool, awesome. Leo, do you want to go next?
Sure. Hi guys, I'm Leo. I'm working with Heng in the same team in Salesforce. I've been in Salesforce for 3 years, and then I'm interested in dealing with big data at scale. And yeah, that's it. I will be panelist to answer questions as well. Yeah.
Awesome. Thanks, team. So just wanted to let you know that myself, Chris, and Denny will be helping to moderate this talk. And another quick reminder is you can submit questions wherever you're watching this, YouTube, in Zoom, on LinkedIn. So please keep them coming. Awesome. Salesforce team, please take it away.
Sure. Hi, everyone. Today we'll discuss about the global synchronization and ordering in Delta Lake. Okay, so this is our third talk. In our previous 2 talks, we first introduced ourselves, who we are. At Salesforce, we build and maintain a platform to capture the custom activities. So those activities are either consumed by downstream product in real time or stored in our data lake. So this data lake supports the creation of up-to-date dashboards by downstream components like Einstein Analytics, or help the training of machine learning models for our customers who are using Salesforce Einsteins. And in our first talk, we primarily present the major design principles of our pipelines, the downstream incremental read with notifications, and the framework for exact once write across tables, and the optimization to use graph to detect the cascading mutations. In our second talk, we focus on the performance of our critical use case, which is engagement ID mutation. And we discussed our partition strategies, partition by org and Z-order by engagement date. And we also elaborated why we choose IO pooling with data skipping and Z-order over partitioning pooling. And we also share our ID mutation benchmarking results. So after all this design in place, we are able to run our ingestion, mutation, and data retention job at scale. In our beta testing, we observe, however, frequent errors of conflicting commits that fail our pipeline. So we find that while Delta ACID transaction maintains data integrity, there's no good way or mechanisms to resolve the right conflicts. So today's agenda, first, we will walk through our pipeline in more details. and take a close look at the conflicting commits error and try to understand in two levels, one level from Delta Lake, and second level from our pipeline itself. Then we will present the root cause and the solutions and the results for this problem. So this is our pipeline for engagement data. So in the middle is our Delta table, engagement data table. And on the left is our engagement ingestion job, which takes the engagement from our Kafka string and append them into the table. And on the right is the engagement ID mutation job, which takes the mutation request from another Kafka streams and perform the mutation operations on the engagement table. And in the middle is our data retention job, which performs the GDPR TTO request from a third Kafka streams. So the engagement data table at high level has three columns. The org ID is the petition column, and the engagement date is the Z order column, and the engagement is a structure with the detailed fields of the engagements. One of them is the ID, which unique identify engagement. And the mutation request table, the ID, org ID, and engagement date is used to join the main engagement table. And the mutation operation could be convert, merge, or delete. And the key is the ID of the engagements, and the insert record is the new engagement record if applies. So just touch a little bit about the mutation operations. If it is a new audience, so when each of the engagement activity has an owner, so it's a person. So when a person's role becomes, say, from a lead to a contact, it will have a new ID, and all the engagement that belong to that person will have a new ID as well. So as a downstream, we have to handle that situations. So this is called a convert. And this is our query pattern for ID mutation with the three columns. The org ID engagement date is associated with petition and the files. And the key, the ID, is to identify which engagement record it is. For our data retention tables, these fields are specific to our data policy services, but we only care about two of them. The scope field is a struct. It has an org ID to join to the engagement table, data table. And the upper bound time is used as a TTO time for the data retention job to delete all the records that is older than this time. So the query pattern for data retention looks like first is joined with org ID, and second is compare the engagement date with upper bound date. So the problem is the conflict commits error occur when two jobs concurrently write to engagement table. So this is the example of this error in stack trace. It ended up with the exception called concurrent delete read exception, and with the error message of saying this transaction attempt to read one or more files that were deleted. And give the example of the files with the petition, and it asks to please try the operation again. And this is the stack trace from ID mutation job. And this is another example from the data retention job, which have similar error messages. And also you can see it also gives the conflicting commits details, which we'll take a close look at later. So we will try to analyze these conflicting commits in two levels. So first, let's start with the Delta Lake level. In last talk, we discussed how the Delta perform writes, Delta perform version writes. For example, for file A, if we want to change, apply some updates to this file A on version 3, it first copy a snapshot from the version 3, applies the updates, and write it back that becomes version 4. So this is for the single updates. When it comes to the concurrent updates, multiple jobs or threads or process try to do the same to create a snapshot of the copy of version 3. and do the updates and try to merge when it commits. So the committing conflict happens in the phase of merge and resolve, which is controlled by the Delta Lake isolation levels. So far, Delta Lake provides 2 levels of isolation. One is the serializable, and the second is the write serializables. In serializables or write operations, insert, append, update, delete, and merge commits has to happen sequentially or fail. And in write serializable mode, insert and update or delete or merge can commit concurrently. So serializable level, isolation level is the strongest one. So in this mode, operations are allowed as long as there exists a serial sequence of executing them one at a time that generates the same outcome as that seen in the table. So simply speaking, that we are not allowed to have 2 write operations commit together in the same overlapped time frames, just showed in this in these illustrations. And the write serialized table, write serializable mode is a weaker isolation than serializable, and insert and one of the write operation, update, delete, and merge can commit concurrently. So in write serialized table, for example, here the update happens at 3 time 3 and end at time 8, and another insert happens at time 5 and end at time 7. This kind of operations can be is allowed. To make it more specific or clear, Databricks provide a Delta Lake concurrent control matrix, which indicates what operations can conflict in what mode. So insert, there's no way to conflict, and insert with update, delete, and merging too can conflict in serializable, but cannot conflict in write serializable. And the insert and optimize cannot conflict. And for update, delete, and merge and themselves, they can conflict in both mode, serializable and write serializable. And and optimize and with them, they both can conflict in both mode. So and optimize to optimize, they can conflict in both mode. So after understanding the way that Delta Lake do the writes and the isolation levels, it'll be more clear if we revisit these errors. So from the stack trace, the error ended up with, so this is an example between the data retention delete and the ID mutation merge conflict. So you end up with the concurrent delete read exception. And it gives the example of the what files that has these conflicting commits. And in the conflicting commits details, you can see the operation is merge. And it also indicates the predicate, which is the query pattern for our ID mutation case with the join of delete keys, org ID, and engagement date. And they pointed out what job name has the conflict with the current job and indicate the isolation level, which is write serializables. So from the Delta Lake, we know like Delta do the version writes, and which is controlled by the isolation level. And the concurrent control matrix tables indicate what 2 operations could conflict in what mode. So let's continue to look at the pipeline, our pipeline itself. From the pipeline diagram, you can see there are 2 aspects of our pipeline. One is the independent process stream, and the second is the process orderings. So independent process stream means each of the job consume the stream from a different Kafka topics, and at different levels. So at different intervals. So this the interval of frequency is decided by our SLAs. So for example, our engagement ingestion and ID mutation run hourly. So we run them in the trigger once mode, but it's the structure streaming job. And our data retention is set to run daily. So if needed, we can change the frequency of engagement ingestion or mutation to run more frequently, like to run every 15 minutes or 30 minutes, which is decided by the SLAs. And the process orderings. So our engagement activity has a life cycle with an order. So first, it is created, and second is subject to mutated, and the third is TTL'd. And we expect the same order in the arriving time of those engagement activities, mutation, and TTL requests to our Kafka queues. And we also expect follow the same order for the process of the three streams. And this is the happy path. So if there is a disorder due to some system glitches or other reasons, we have a retry mechanism to handle the disorder situations. So for example, the mutation requests arrive before the engagement activities, like that. We use a very simple scheduler to apply the ordering. So we split our three jobs, we split the hour into three parts and schedule our ingestion job to run every hour at 00 minutes. And we schedule the mutation job every hour and run and trigger at 20 minutes within an hour. And we set the data retention job daily at 11:40 every day. So this is a very simple mechanisms to apply the orderings. And for the disorder retries, we can zoom in our ID mutation pipeline. So we do not directly read the mutation requests from Kafka Stream and apply them into to the table. Instead, we first stage the mutation request to our mutation request table, and the mutation ID and engagement ID mutation read this table in a file stream. At the same time, it also reads another table called mutation request retry as a string as well, and merge these two streams and apply the mutation request to engagement data table. If the ID mutation job cannot find a key in the main data table, it will write this request back into the mutation request retry table, mark it as not found. And the next time it will retry those requests in the retry table until it reaches the maximal number of the retries. So this is the way we handle the possible retry and the disorder situations. So these two, by analyze our pipeline, we understand the two characteristics of our pipeline. One is independent stream, and second is the process ordering with a simple scheduler. So the root cause we conclude is that the simple scheduler is not reliable. It could, two jobs or jobs could overlap, has the overlapped running window. If one of the jobs run over 220 minutes, and which caused the concurrent writes, and decided by the delta isolation level, and could possibly end up with committing conflict errors. Now with this our root cause, we have multiple options for solutions. One is partitioning and disjoint command conditions. And second is apply the orchestration tools. And third is apply the dispute lock and use the compare and swap. So let's look at these three options one by one. For partitioning and disjoint command conditions, this option is available on the official Databricks Delta documentations. The idea is to appropriately partition the data and avoid two operations to add in disjoint command conditions. So for example, if our table is partitioned by date, and the two operations below will not conflict. So when we update the table with a date is greater than 2010 January 1st, and we do a delete table where the date is less older, less than the 2010 January 1st. So this option does not for us because of our partition schemes. So our engagement data table is partitioned by org ID and Z order by engagement date. So because of Z order, the data is clustered into file chunks in a range of engagement date. And we have no control of this kind of engagement at the range of engagement date. So which means the updates could still be applied to the same data file because of the Z order clusterings. I borrowed the tables from our last talk of performance. And you can see that this is the data file within one engagement, within one partitions. Take the first one, for example. So this file has all the engagement records from the engagement date 2019 August 16th to 2019 August 27th. And it is possible that our data retention job apply a TTL operations that is older than the 2019 August 20th within this file. And at the same time, the mutation job apply the mutation operations on the engagement record on 2019 August 26th. So, which means, and also, it's very difficult for us to control the predicate with unoverlapped range across two independent stream processes. So we think that this solution does not work for us. And the second one is we can rely on some orchestration tools, such as Airflow, and operate our process stream as a DAG. It's a very simple DAG. It will be which run in sequential in this order. First is ingestion, second is mutation, and third is TTL. So we think this solution could work, but with limitations. So first, as we run our pipeline as a DAG, we bound all the streams to run at the same pace, which has to satisfy the highest SLAs. So this could cause some empty processes, like for engagement, TTL or data retention, because the TTL per org request only send once per day, which is kind of the waste of our resources. And the second, naturally, our pipeline handles independent, has an independence characteristics. They consume the Kafka streams from two different Kafka topics, and it does not necessarily constitute to a DAG. So we think even though we can do that, but naturally our pipeline does not fit a DAG model. And third is that we lose the option to run them continuously in micro batches. So finally, we decided to use a distributed lock and for the synchronization, and use the compute and swap to apply the orderings. So we think that our pipeline design, given the pipeline design, we think that the conflicting commits issue fall into a race condition and locking model. And the shared resource is engagement data table. And the streams, the different jobs are the threads modifying concurrently. To apply the ordering, we borrow the concept of computer and swap, which is very commonly used in concurrent programming. So the SAS is an atomic instruction used in multi-threading to achieve synchronization. So it compares the content of the memory location with a given value, and only if the value are the same, and modifies the content of the memory location to a new given value. So we will see how we leverage this compute and swap concept to apply the ordering in our pipelines. So we create a very thin layer on top of our jobs called job coordinator and apply the job coordinator to all our jobs at the framework levels. From the configuration of job coordinator, you can see how it works. So the job coordinator takes 3 parameters. The first one is the log name, which indicate what resources we want to protect. It is usually the data table name. For example, this is the engagement data table name, engagement HVS data. And second is the job itself, the job name itself. For this example, the configuration for ID job, ID mutation job, it will be the mutation. And the third is the predecessor. So which defines for me what I should run after my previous job. In this case, the mutation job is set to run after the ingestion job. So this is how the job coordinator work in the workflow. So first, our streaming job starts, and the job coordinator is initialized with Zookeeper. And then the streaming job pulls data from Kafka periodically and starts the micro batch process when message arrives into Kafka. So within each of the micro batch process, the job coordinator first try to obtain a distributed log with the given resource name set in the log.name. And if it cannot find a log, obtain a log within the given name, it gives up, timeout. And the next pool will start from the last checkpoint because this is actually an empty ROM. So once it obtains a log, so first it will read the predecessor field from the Zookeeper and compiles it with the expected one, which is set in the predecessor configuration. And if the predecessor is not expected, it will give up this term, which means it's not his turn to run, and release the log. And the next pool still will start from the last checkpoints because it is still an empty run. And if the predecessor is expected, then it will register his name itself to the Zookeeper, which is set in the job.coordinator.name. And it proceed with the micro batch process. And when it finishes, it will save the checkpoint. And after all is finished, it will release the log. So overall, this is how the job coordinator works. And so the predecessor defines the ordering of our 3 pipelines. So we want to have our 3 pipeline run in this order: ingestion, mutation, data retention, and so on. So then in this case, we have to configure our predecessor for each jobs like this. So ingestion could be a no predecessor, could be a mutation, could be data retention. And mutation must have a ingestion, must be to ingestion as a predecessor, and data retention must have a mutations. And the API of the job coordinator is simple. It has 3 APIs. One is log, is to trying to obtain the log from Zookeeper. The second is the unlog, which is to release the log to the Zookeeper. And the third is the register, is to register the itself into the Zookeeper when it obtained a log and allowed to proceed. So after we have this job coordinator and we want to test whether it works or not. So in order to test it, we create 3 jobs to simulate the ingestion, mutation, data retention job. And inside each job, it does nothing but just sleep for a random period of time from 1 to 15 minutes. And for each time, we capture a micro batch start and end time. And then we set up 2 groups for comparisons. So group A is with the job coordinator disabled, and group B is with the job coordinator enabled. Then we run for a week. And then we visualize the data of each of the micro batch start and end time. So you can see here, this is the result of the group A with the job coordinator disabled. You can see that many of the areas have multiple jobs run in overlapped windows. So here, for example, the delete one, okay, the append means the ingestion job, the mutating means mutation job, and delete means delete job. And here you can see in this window that all the jobs are run in the same time frame. And we can actually visit this graph interactively. So you can see many without a job coordinator, there's no constraint on the start and end time on each of the job. So it's we can see very frequent overlapped running across these three jobs. So here the append run along with the mutate, and here the same thing. Okay. So this is group A. And let's go through group B with the job coordinator enabled. So in this screenshot, you can see each job is pretty aligned, and you don't observe any overlapped window across two jobs. And again, this timeline is available interactively. So you can see this delete run just before the append, and followed by mutate, no overlapped window. And also, everything works pretty fine. So with job coordinator, we no longer observe the conflicting commits errors in our engagement data table pipeline. And at the same time, we also apply the same job coordinator mechanisms to other pipelines of our data lake, containing different sales activities, such as voice insights, and we also know commit errors, conflict commit errors occurred in those pipelines as well. Okay, so far I think we have presented the whole picture of our pipeline with Delta Lake. And we are trying to build a high performance mutable data lake with Delta Lake. And in order to do that, we first make our pipeline as an independent stream process to support, for example, engagement data table life cycles. So the life cycle is ingestion, mutate, and TTL and deletions. And we control the frequency of each of the job or pipeline to satisfy the SLAs. And second, we use notification table to our downstream for incremental read. And we also work to generate high throughput transactions in our critical case, which is ID mutation, engagement ID mutations. So in the application layer, we optimize on using graph to detect cascading ID mutations, to optimize our processings. And at the data layer, we partition by org ID and Z order by engagement date to make our engagement data table or file evenly distributed across reasonably sized files. And we choose to use IO pruning with data skipping and Z order over the partitioning pruning to boost the query performance. While we are able to generate high throughput transactions, we also want to maintain high quality of data consistency and integrities. In order to do that, we create exact ones right across table framework to deliver the atomic write semantics across different tables rights. And today we create a job coordinator to apply this global synchronization and ordering for our independent process streams. We think that we create a pattern to build a high performance mutable data lake using Delta Lake. So because once we have the example of engagement Delta Lake, then we apply the same similar pipelines or mechanisms to other type of data, like invoice, voice insights, email, and meetings. Some of the pipeline may differ a little bit. For example, they may not have item mutation case, but have a usual CDC case with a value mutated, or they don't have it, or the data is totally immutable But overall, we follow the same patterns and mechanisms to make sure the performance and stability and the data integrity. Okay, and the next talk, we'll switch a gear a little bit to discuss about our continuous integration and continuous delivery. And we'll more focus on the Databricks as a platform and how the APIs and the DevOps support to support our CI/CDs. And we also specifically will discuss 2 new development patterns where we formulated when we do the Delta projects. One is the namespace deployments, and second is scenario-based testings. And these two development patterns contribute to the core framework of our for the integration testings and for our Delta Lake projects. That's all from me. Thank you very much.
Perfect. Thank you very much, Heng. That was an awesome presentation. We're going to shift it over. Hey, Craig, why don't you go ahead and start us off? We've got a couple questions, but before I hand it off to you, Craig, I did say, hey, if you have any questions, we're monitoring LinkedIn, YouTube, and Zoom right now. So please ask your questions and we'll do our best to answer them. So Craig, why don't you take it away?
Cool. Thanks, Denny. So our first question comes from Anurag and Leo. I think you might be the best person to take this.
Sure.
So the question is, how is it handling late arriving data? So how is your pipeline handling late arriving data, and what are the limits, if any?
Okay, so I think like for our data, so the only like kind of late arrival case is so we have the actual the engagement data, and we also have like the mutation data, right? So the only late arrival case for us is when the mutation data arrives earlier than the actual ingestion data. It could be like the ingestion pipeline has delay or what for whatever reason. So in that case, we are going to detect that, okay, there's no engagement record in our data lake. And then we are going to keep that mutation data for some time. And then we are going to do the retry to like a maximum number of times. I don't remember exactly like how many, but the time just depends on your like use cases in business logic, like how much time do you need. And yeah, I think that's how we handle that. So this kind of late arriving data topic can be really big. So I'm not sure what's the perspective of the attendees to answer. Like it could be like he's asking like the transactional data, and then but our data model is not kind of transactional model. Yeah.
Awesome. Thanks for that, Leo.
Perfect. Thanks very much. Okay. Well, then I think we've got another question, and I'm actually going to ask either Craig or Fish to answer this one. And so I believe it's from Niladri Dada from LinkedIn. The question is, you have a SQL background and you're a data engineer. You're very comfortable writing Spark SQL statements rather than data frame Spark SQL functions, both for Delta as well as normal PySpark logic. He wanted to understand if there's any difference in performance between these two.
That's a great question. Yeah. So under the hood, both Spark SQL and Spark Data Frame code, they're both going to go to the Catalyst optimizer, and they're both going to get, run through the normal Catalyst process of comparing different plans and determining the optimal physical plan. There can be differences though in the plans they produce. And what I would say is that typically the data frame API will give you more control, and you may be able to optimize the resulting plan a bit better. But for kind of generic workloads where you're doing simple aggregations or joins, typically Spark SQL and data frames will produce the same plan and will run the same. Yeah.
Excellent. Perfect. Well, I believe that's all the questions we actually have for today. So what we're going to do is we're probably going to close up shop a little early, give us a little time back. So we're going to hand it off to you, Karen. But before we do that, I wanted to say thank you very much again to the Salesforce team. Thanks to Craig and Fish for answering the questions, and of course to Salesforce folks. Don't forget, part 4 is in 2 weeks. And note that this will be half the time, obviously, presentation, but the other half very much Q&A. So all the questions that you have, we'll definitely pull some of the old questions we had too, so that way we can go ahead and answer them as well. But any new questions you have about the entire 4-part series, I'd love to have you go ahead and chime in. So I think that about covers it. Karen, anything else that I missed?
No, I think that's good, Denny. Thanks for that. I'm actually I was grabbing the link to the 4th part, so I could drop that in the chat for everyone. So hopefully you'll join us in 2 weeks. So with that, I'll just like to thank our speakers again from Salesforce. Thank you so much for joining us again. And thanks everyone for attending. And hopefully we'll see you in 2 weeks for part 4. So thanks everyone. Take care.
Yeah. Bye-bye.
Bye.
Take care.